So once again, welcome back, and in this lecture we will talk about the force between two parallel current carrying infinitely long conductors. Okay. And thereafter, from the results, we will define the unit of current, and that is ampere. Okay. Look here. Look at this green line. This goes to infinity, and this one also goes to infinity. It comes from infinity, and this also comes from infinity. So they are a set of wires which we can call, give them a name, number 1 and Mr. number 2. Okay. Now, as per what we have learnt in the due course of time, that let us consider this wire carrying a current I2. I2 can be larger than I1, can be smaller than I1, can be equal to I1, it doesn't matter. So with that, let us see. At a distance d away from it, there is another wire. So we are not concerned about the wire. We are concerned about the magnetic field. So there is the right hand rule. I hold the wire in my right hand. I hold this wire, is carrying current like this in my right hand, with my thumb in the direction of the current. What happens is that the magnetic lines of field, they will, on this side, they will be out of the board. Okay? And of course, on this side, they will be into the board. Right? So this B2, the magnetic field due to this current at a distance d away from it is B2. So all over this wire, the magnetic field is the same, B2, 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 like that. Okay. And with a similar argument, when I hold this like this, as I told you, that B1 will be into the board, into, and therefore all on this wire, the magnetic field is constant and it is equal to B1. Okay. So this is one thing, one result which we are recalling from the past is one thing. Now, I will first of all qualitatively show to you that the force on wire 1 due to wire 2 and the force on wire 2 due to wire 1, they will be towards each other. That means attractive, and later I can show quantitatively, first qualitatively then quantitatively, that the two forces are equal and opposite, just like in the case of Newton's third law, F12 is equal to minus F21. Okay. Now, let me tell you the rule that I am going to use. The rule that I am going to use, I have called this open palm rule. Okay? And in the open palm rule, I told you that if the charge on which we want the force is negative, then I am going to use my left palm, open left palm. And for a charge which is greater than 0, I am going to use my right hand. Okay. Now, conventionally an electric current is supposed to be a flow of positive charges which it is not. It is the flow of the negative charges in the opposite direction. Both the things will touch upon. Okay. Now suppose I call here. My charge is positive. Okay. And the charge therefore will be moving along the direction of the current. The magnetic field direction is like this. Coming towards you. And my right hand, my thumb is pointing in the direction of the fingers in the direction of magnetic field, and the outstretched thumb is in the sense of I. I have not used the word direction purposely because electric current is a scalar quantity, will not have a direction, but will just run away with the word sense. Okay, now look here. Here is a positive charge which is moving in this direction. Okay, the magnetic field is like this, towards you. Then the charge is moving like this. Then the pushing direction of my palm, the pushing direction of my palm is like this. So on this charge, which has the mass of course, there will be a force which will be applied from the wire 1 to wire 2. Okay, like it has been shown over here. If the same thing we see for the second wire, then you can see that the magnetic field is into the board. And this is a positive charge, I am still using my right palm, and the charge is going up like this. So the pushing direction of my palm becomes what I have shown over here. Then the two, for the positive charge also, for the positive charge on the other wire, they are in the direction of pushing direction of the palm. So they show a kind of an attraction, the charges. Now let me take a negative charge, which is the case. An electron is basically moving with a certain drift velocity, and that is what gives us I1. So friends, now I'll use my left palm. Okay, and the direction is like this. Okay, the direction over here is like this. So what I get is, but the charge is moving. Okay, the direction is like this, but the charge is moving in the downward direction. In the downward direction. I have a little difficulty in showing it to you, but when you are doing, you can do it. Do it. Okay, then what happens is that the pushing direction of the palm is like this. So the negative charge also gets a push towards the second wire. And similarly, in this case, I have taken a negative charge. Similarly, so what is the magnetic field, which is here? The magnetic field is into the board. Okay. And look here, it's very simple. The magnetic field is into the board, and my negative charge is moving down. Okay. So the pushing direction of the palm is towards this wire. Of course, both wires are in the plane of this board. So in either case, whatsoever is the contribution, whatsoever kind of charges are there that contribute to I1 and I2, they will have an attraction towards each other. This is just a qualitative thing that I have shown to you. Okay. So pushing direction of the open palm gives the force on the charge. Okay. Now let's see that B1 will be equal to how much? This we have already derived, mu naught I1 upon 2 pi d, and B2 mu naught I2 upon 2 pi d at the, as they have been shown. Okay. So now There is another formula that we had. The force on a length of wire L, and which was found to be ILB, okay, but my teacher said bill, okay, so I'm using that bill here, bill sine theta, and sine theta is equal to 1. So the F12 becomes equal to B2 into I1 into L for a length L of the wire. That will eliminate later on. And F21 on the second wire due to the first one, it will be B1 I2 into L, just like that, divided by, so no, divided by, so B2 I substitute here, mu naught I2 into I1 into L upon 2 pi d, and here mu naught I1 upon 2 pi d I2 into L. Now look into these two expressions. The two expressions, they give the same results. The only thing is I1 and I2 they are shifted, it doesn't matter. So what we have found, even quantitatively, so let us combine the qualitative discussion with the quantitative discussion, and we find that F12 and F21 are equal and opposite. Let's call them F, the force, F, say. So the force is attractive in this case when the two parallel currents are in the same sense. Okay. Now, I leave it to you to show right from the beginning that for anti-parallel currents, this one is going like this and the other is coming like this, there will be a repulsion. Okay. So you start from the basics that I have told you, and you arrive at that, satisfy yourself, and then respond to the result that I have given to you. Okay. Now, this force was taken as equal to F on a length L of the wire, either this wire or that wire. Okay. Let us divide this F by capital L. So I'll get small f, which is force per unit length of either wire. So the force per unit length either wire turns out to be a beautiful relation which only consists of I1, I2 and T. Okay. F is equal to mu naught I1, I2 upon 2 pi d. So this force per unit length is proportional to the product I1, I2, or you can say it separately, proportional to I1, proportional to I2 and proportional to 1 upon D, like we have been doing several times, and we get the result F is equal to mu naught I1, I2 upon 2 pi D. I am running out of space. So next I am going to discuss many things about it and then push for the definition of Ampere as to what will be that. So we have this formula, the force per unit length, small f is equal to F upon L in newtons per meter, and the formula is mu naught I1, I2 upon 2 pi t. Okay. Where we learnt that parallel currents attract and anti-parallel currents, they repel. Okay. Now we go for the simple definition of Ampere, which was discussed, deliberated upon and adopted in the year 1946, 1 year before I was born. At the time when Germany and Japan were defeated in the Second World War, where millions of people were killed, wherein, and the Indian markets were floated by a couple of things from Japan. One was the lamp, which is called lantern, and the other was Jim rickshaw. The rickshaw that we have, that is a Japanese product, and initially it was called Jim rickshaw. Okay, so just to amuse you. Okay, so the people put their heads together and they defined ampere, wherein they took two currents in the same direction. I1 is equal to I and I2 is also equal to I, and to a 1 meter length of these currents. Then they found that the force F, this I can write as, when we take I is equal to 1 ampere, so this becomes equal to 2 into mu naught upon 4 pi. Actually it is mu naught upon 2 pi. So I write it as 2 into mu naught upon 4 pi into 1 in the numerator and into 1 in the denominator. So the force between these two wires, the attractive force between these two parallel wires, turns out to be equal to 2 into 10 to the power of minus 7 newtons per meter, because mu naught upon 4 pi is equal to 10 to the power of 7 minus 7. And I told you that that is an assigned value, it cannot change. That is an adopted value, an assigned value. Not like 1 upon 4 pi epsilon naught is equal to 9 into 10 to the power of 9 Newton meter square per coulomb square, etc. Okay. But when this kind of a measurement was made, one of the things is that IFF, mathematics is stand for if and only if the magnetic field due to the earth, which is always present anywhere, that has to be reduced to 0. That has to be eliminated by some means, and there are means to eliminate that thing. Okay. The force measurement is carried out by a instrument, an instrument which is called current balance. In Arabic we call an instrument a jahaz. Okay. This is also can be measured by several means, and one of them is Roget's spiral. You can search, and if you want to look for that, you can search that. So 1 ampere, it turned out to be 1 coulomb per second, or 1 coulomb was now defined because ampere became the one of the 7 fundamental units. Okay, length, mass, time, temperature, and now ampere, and other units will come when we teach other things. Okay, that is the way. Once again, I emphasize that you use the palm rules. The palm rules, where, for example, here I can say that the negative charge which is moving like this, okay, and the negative charge over here which is moving like this, they are like this and towards each other. The open palms are towards each other. Just a little bit of practice will land you in a very happy situation. Then you will not have to use the left hand rule, because left hand rule, the use of left hand rule is a little cumbersome. Okay, because we are dealing in quantities which are vector quantities, therefore we have to resort to rules like left hand rule or open palm rule, which I told you is the thappa rule. Okay. So with that, I come to an end of this lecture. I insist that this should be thoroughly understood in terms of, and if you care, then how many charges are there in a certain length, that you can find with the number density multiplied by the value of the charge and the area of cross section into length, that will give you the volume. And VD, that value, etc., you can take and understand this. Before I just part from you, I would like to say that if you understand that, then many a problem where we can ask you to calculate the value of the force per unit length, or value of the force for a length of 2 meters, 5 meters, 7 meters, like that, etc. When the separation is 1 meter, 2 meter, half meter, 5 centimeters, etc., etc. And this is the way that we test you if you can do the things quickly or not. So that is the generic things about setting questions for you to solve. But if you are well versed in this, if you remember this formula, which is easy to remember, okay, and of course BIL, sine of theta, okay, mu naught I upon 2 pi d, that kind of formula. So this is all a set of formulae which have been used in this relation. And next we learn about more things in the next lecture, and particularly about what we call torque on a current loop. Okay, that is the genesis of what we call when the torque is there, then there is a rotation, etc. Genesis of galvanometers, ammeters, voltmeters, all those instruments, all those jahaz that we have. Okay, thank you very much.